All right, passing environment variables. Every process has a set of environment variables. These are the values you see when you type set or env on the command line. I think for Linux, you don't need to do that. You just need to do your, I think you just do export like this, or you can just do the port equals 2000 and your program. Yeah, like this. This is the Linux way to do it, and I think in Mac it's the same thing. I don't think you need to do set. And they usually tell the process useful information, such as the location of the home directory or where to find the commands. C programs can read environment variables with the getenv system call. You can see the getenv being used in the diner info program on the right. So right here, getenv juice. So juice is an environment variable that gets set before you run the program. If you want to run a program using command line arguments and environment variables, you can do it like this. So you can create a set of environment variables as an array of string pointers. So create an array of strings. Then just do, I guess it's simple. Just pass. So each string is going to be your environment variable, but then the last item has to be null. So this is how you can manually do it. And then when you do exec with the program you want to run, you can just call the program with some arguments. And remember, null at the end of the list of arguments. And then finally, the environment variables you want to exist when you run this diner info program. And here's the diner info program here. See how it accesses the getenv, it calls getenv to access the juice environment variable. So the exec le function will set the command line arguments and environment variables and then replace the current process with diner info. So you actually don't, like, to tell you the truth, getenv isn't just limited to programs that were started up from exec le or exec whatever from the previous program. You can use, I think you can use getenv anytime you want to access environment variable. So if I can just like write, I'll just write like a simple program right now to show you. So I can do something like maybe new folder and demo. Okay, so let's do this. Let's do include stdio.h, include stdlib.h, and then let's have a main function. Okay, oops. Return 0. Okay, so let's say this. Getenv is going to get us back what? Getenv. It's going to give us back a string. So basically the value of the environment variable. So you know how like in our way back we had an environment variable set for our Node.js server, like port. We can actually do the same thing in our C program. So I could say something like this. Port as string getenv port if not port as string, or let's just say port as string if they don't have anything inside here. We can say port as string is equal to 3000, for example, and then we can just say int port equals a2i port as string, and then we can print out the port number is, oops, yeah, okay. And then, so this will be the environment variable port. And if we don't have one, I think it'll be 3000 by default. So let's do that. And demo. Okay. So the port number is 3000 because we didn't set any environment variables. But if we did something like this, port number is 1234. So we've accessed environment variables by just using getenv. Has nothing to do with this exec le. I'm just showing you that you can just access it anytime using getenv, and that's very useful for your C programs. You can actually export variables too, like this, for the current shell session. So maybe 4555, and then you can do a.out, and it'll be 45555. You can also change that in your bash RC, for example. Let's just do maybe all the way down here. Then we'll do something like export port equals 8888. And then we can source bash rc, and then we can do a.out, and we'll have 8888. So many ways you can do this actually. But yeah, I just wanted to call out that it's not just limited to exec to getenv, and is something that's general. You can do for your programs. So Um, yeah, so the exec le function will set the command line arguments and environment variables, and then replace the current process with the diner info. So remember, exec, when you call a program like diner info, it actually takes all of the diner info executable data and replaces your current process, your own program that called it. Uh, anyway, but what if there's a problem? If there's a problem calling the program, the existing process will keep running. That's useful because it means that if you can't start the second process, you'll be able to recover from the error and give the user more information on what went wrong. And luckily, the C standard library provides some built-in code to help you with that. Okay. Most system calls go wrong in the same way. Because system calls depend on something outside your program, they might go wrong in some way that you can't control. To deal with this problem, most system calls go wrong in the same way. So they crash, or like they give some sort of error code in the same consistent way. The exec le call, for example, it's really easy to see when an exec call goes wrong. If an exec call is successful, the current program, the one that you invoked exec with, stops running. So if the program runs anything after the call to exec, there must have been a problem. So let's do that. Let's do a test. Okay, so let's do exec demo maybe. Okay, so start that up again. Where's my V? Oh, I'm using the wrong finger. Huh. Where am I? RV. Split keyboard. Okay. Now, let's see. Let's call exec. So we can make up a program. Let's make up a program that doesn't exist. Let's just say program name is going to be caddy. Okay, and let's do this. Let's actually create a file here. We're gonna make overall. It's just gonna be, we're expecting to use cat to print out this test.txt. That's all we're doing. Anyway, program name is caddy, and let's do exec le program name, and then the first arg is also a program name, And then we want arguments, so that'll be null, no arguments. And oh wait, we do want arguments, sorry. It'll be test.text, and then end our arguments, but we don't have any environment variables, so I think that's just null here. And then this exec le exists in unistd.h, so we have to include that. And then since we don't have the program caddy, we should expect this to execute here. This puts here. So this only executes if the exec le call fails. And remember, this exec le call will fail. By design, we're making sure it will fail because we're calling this program here, which doesn't even exist in our system. So the exec le call failed. Okay. Now let's compile. Okay, let's run it. And the exec le call failed. I forgot the D. So that's expected because we don't have a program called caddy. So this puts after the exec le was executed because this program never got replaced by the program that we wanted to call using exec. But if I change this to cat, for example, which we do have, so the name of the program, and then the program again for the first argument, and then the real argument to that program, which is the test.text, then null, no environment variables. So, oh, still failed. Why? Did I say cat? Or did I use the API wrong? Oh, it should work. Let's see. Exec le, is it because we don't need, is this maybe that? Empty array? Oops. Something like that. Let's see. What? Let's just do regular exec. Why doesn't it work? Did I use it wrong? Okay, let's just do exec. So let's go back to caddy. Undefined reference exec. Oh, exec L? Exec L without the environment variables. That's why. Okay. We gotta do it. We gotta do it again. Because I'm just like randomly doing things, which is bad. Okay, so caddy failed. And then now cat. That should work. Right? Why didn't it work? Is it because you can't find test.text? Why? Let's see. Path. Oh, it's exec LP. Maybe. Ah, I got bit. Okay. Start over, everybody. Thank you for being patient. Okay. Why exec LP? Remember. I got tricked because exec LP takes into consideration of the programs in your path variable. Otherwise, every time you start up a program, it has to be the full path to the program. So for example, which cat? User bin cat, okay? So this would have worked for exec L, for example, if I had done user bin cat like this. Because that's the full path to the program. So if I did if I did gcc a.out, that worked, this hello world here. Okay, so that worked. And the reason why exec, I think it was LE didn't work before is because we didn't have environment variables, but we're required to give environment variables. We don't have it, so that's the reason why I chose exec L. So we're good there. Now, if I did caddy here, this wouldn't have worked still because we don't have a program called that. So exec failed. So that's why I went to the puts down here. Okay. But the problem now is that I didn't do it this way. I did it this way. I assumed, that the program could have been found in the path variable. So just to, our path variable is this. All these directories here for our shell to be able to find programs. So this exec L failed because of that, even if we corrected to cat, for example. Oops. Still failed because we didn't tell exec to search for the path, which is the P version. Ooh. Tricky right here. Wow, okay. So that's something we have to remember, that these exec type functions, how we use them and which ones we choose really do matter. Okay, so yeah, so I wanted to show what that looks like if our call fails and if our call is successful. So your call to exec works if the code under it doesn't execute, and the code that the program that you called executes instead because it takes over. If it doesn't work, then your code will still run after the exec call. Okay. All right. So we're there. But just telling if a system call worked is not enough. You normally want to know why a system call failed. That's why most system calls follow the golden rules of failure. Here's the golden rules of failures. Tidy up as much as you can. Set the error number variable to an error value. Return -1. So give some error code. The error no variable is a global variable that's defined in error no.h along with a whole bunch of standard error values like eperm1, no ent, so no such file, no entity maybe, error no entity equals 2, esrch, so error, I don't know what srch is, but no such process. Oh, no such process. No such, I don't know. Okay, and then mullet, bad haircut. This value is not available in all systems. I think they just made it up. Okay, so now you can check the value of error no against each of these values. So when something fails, error no will be set. Okay, cool, great. So you can check the value of error no against each of these values, or you could look up a standard piece of error text using a function in string H called stir error. Okay, so if a system can't find the program you are running, it sets the error no variable to error no entity. The above code display the message no such file or directory. Okay, let's try it. All right, I wonder what happens if we do cat blah. Okay, no such file. Okay, so that'll be an error, so that program will fail. But let's just do caddy, and then let's say let's output the error no. Put the error no is %i, so it's an error number. And we just do error no, and we have to import the error no.h. So we output error no, which is printf. Okay, and now we also want to print out the string of the error. Error no message. So the message corresponding to the error no. Stir error no. Okay, so let's do it. Caddy. So we should get down to this code here. And then reach the main. These are warnings. Okay. %s argument 2 has type int. Is it? Is it? What's stir error? Oh, and string h. So we need to import string h too. Okay, lots of stuff to import. Okay, let's try again. Okay, cool. So we do this. Okay, the exec le call failed. We should change that to LP, by the way. Okay, let's do it again, just so that we can read it correctly. Okay, the exec LP call failed. The error no is 2. Error no message, no such file directory, no program that exists. So what happens if we do cat instead? Cat should work. It should display hello world. Okay, what happens if we don't have the right file? No file. Should still execute because that's not a specific error to us execing. It's just an error to cat specifically. So it's up to cat at the point. I mean, we were able to start up cat, and exec's job is only to start up the program. It's only to initialize the program. Whatever happens after that is purely the program's problem in this case. So these errors only come out if we couldn't execute. So we couldn't successfully invoke exec. But as far as errors that the program that you are starting up goes, like cat or maybe Vim, Firefox, the errors that happen after that, after it has been started, that's purely like that responsibility of that program, and we don't keep track of that. So error no will tell you why this call failed. Would have been very useful for us. Okay, so if the system can't find the program you're running, it sets error no variable to e no entity. The above code will display the message, no such file directory. Okay, cool. Different machines have different commands to tell you about their network configuration. On Linux and Mac machines, there's the sbin ifconfig program. And on Windows, there's a command called ipconfig that's stored somewhere on the command path. This program tries to run the sbin ifconfig program, and if that fails, it will try the ipconfig program. There's no need to pass arguments to either command. Think carefully. What type of exec commands will you need? All right. Let's do exec demo 2 and solve the problem. Okay. Oops. Money. stdlib.h. And I'm guessing we need also unistd.h. Maybe string. Okay. Starting to need a lot of things now. Okay. Okay, now, what is it? If, let's see, we're going to start up sbin ifconfig. Okay, so maybe if exec l, the program name is going to be /sbin /ifconfig, and then same thing, /sbin /ifconfig, and we don't have any arguments. So this works. Okay, this works. What do we do? Well, we don't do anything. We just proceed. This, whatever's in here will never run. So this code will never run if sbin if configs is successful. Why? Because it has started up correctly at that point. So after this is done, it'll actually this whole program that's running right now will be replaced by the sbin if config. So technically, it will never run. But okay, if that fails, we want to also do again startup. What is it? IP config. Okay. First of all, do we even have an sbin if config? I want to try something equivalent. ls sbin. We don't even have if config. How about if I do? Okay, so that'll fail. So how about IPA? Yeah, we do have IPA, but we don't have IP config. Okay, so let's do IPA. So IP, and then and we need to figure out the real path, which IP user sbin IP. Okay, so USR sbin IP. Maybe this one's also at USR sbin. Let's check. Nope, we don't have it. Okay, cool. So USR sbin IP, and then remember we had to specify the full path because we don't have the p value. It's not exec LP, it's exec L. So same thing, sbin IP. Let's correct this one here. And then the argument is just to be A, and then null to end the argument list. And then if that, so this code will never run if USR sbin IPA is successful. So here at this point, we failed. SCD error. Oops. Cannot run IP. S. What do you think goes here? Huh. I guess it's just going to be the backup program. Maybe. Okay. Return what? Return 1. And then otherwise return 0. So I'd say something like this. So again, if exec L for this one is successful, then everything under here won't ever run because the program is going to be replaced by ifconfig. But if this fails, it'll try to exec L this one, which is IPA basically. And if that's successful, this code here would never run. But if that fails, then we're going to print out an error message, a standard error. I don't really know what really goes in here. It's probably just some sort of path to the program. But then we'll also return 1. But just keep in mind that we're outputting this error to standard error here. So, okay. Okay, so let's test it. And what is this? Exec demo 2. Okay. Cool. So this is actually the output of IPA. So IPA right here. Right here. You see that? Now what happens if we didn't say IPA? What happens if it was, I don't know, IP config? Like this. Null. Right away. Okay? Let's do that. Oops. Compile. That out. Cannot run IP, USR sbin IP. I'm not even sure what this error message is supposed to be. Let's see. Huh, they didn't even tell us. Okay. That was Okay, so let's correct that back to IP. Correct this back to IP. Let's add the A argument again. We want a working program. Okay, so that's good. Let's see what the answers are. Union STD, we got that. Oh, we need error. Oh, it was supposed to be Erno. Oh, yeah. You see, I didn't know what they were talking about. Okay, so we want to do stir error, stir error, sterno, or not erno. There we go. Could have been that. All right. Why do we even need to check if it's -1? Because if it fails, then it should just go into these ifs anyway. Yeah, I'm confused. Like, why would you even need this equals -1? Because the thing is that if it failed, it's going to execute this code anyway. But okay, fine. And if it's successful, it just executes that code. Okay, well, close enough. We still got a working program, so I'm happy. Okay. There are no dumb questions. Is the system just easier to use than exec? Yes, but because the operating system needs to interpret the string you pass the system, it can be a bit buggy, particularly if you create the command string dynamically. So why are there so many exec functions? Over time, people wanted to create processes in different ways. The different versions of exec were created for more flexibility. Do I always have to check the return value of a system call? Doesn't it make the program really long? Yeah, if you make system calls that don't check for errors, okay, fine. That's fair. That's what we didn't do. We didn't check for this error return code. Okay, fine. It will probably have more bugs. It will probably, yeah, probably shorter code, but it will have more bugs. It is better to think about errors when you first write code. Okay. To be fair, I didn't do that too, so it would make it much easier to catch bugs later on. If I call an exec function, can I do anything afterward? No. If the exec function is successful, it will change the process so that it runs the new program instead of your program. That means the program containing the exec call will stop as soon as it runs the exec function. Okay. Bullet points. System calls are functions that live in the operating system. When you make a system call, you are calling code outside your program. System is a system call to run a command string. System is easy to use, but it can cause bugs. The exec system calls let you run programs with more control. There are several versions of the exec system call. System calls are usually but not always returning -1 if there's a problem, and they will always set the error variable to an error number. All right, so the guys over at Starbuzz have come up with a new order generation program that they call coffee. So it's a coffee program. So int main, int argc, or that. So it's going by environment variables. Okay, so there's gonna be an extra environment variable. So there's a extra equals blah. Here's a food equals blah, and then extra equals blah again. So all right. So if there isn't any environment variable set, or if there isn't any value set in the environment variable called extra, then it's going to try to find it in the value inside the environment variable food. And if there still isn't anything, see how it's reassigning W here, then it's just going to find the argument passed when you're running the program as like a last desperation move. And then after that, it's going to try again to get this value from the environment variable extra. And if there isn't anything, it's going to try to see if it's accessible as the last argument of the program. So not an environment variable, but rather the argument that you passed when you run the program. And then it's just going to print out the string, S with S. Okay. Okay. So to try it out, they've created this test program. Can you match up these code fragments to the output they produce? Okay. So, okay, sure. So it's just going to be the code that goes in here and what it's going to be the output. So, all right, coffee is going to be the food. So food. So there's going to be no extra, but then W is going to be used. W is going to get assigned by the value set by food because that's set. So it's coffee. And then it's going to see if there's an extra for C. Okay. So then if not, it's going to use the last argument. So for this one, it's going to be the last argument is going to be donuts. Food is going to be coffee. So it's going to be donuts with coffee, I think. Donuts with coffee right here. This one is going to be, what is it? Food is gonna be donuts. So it's gonna be the order. You gotta pay attention to the order here. It's a C and then W. So it's gonna be C with W, even though W gets set first. So that's why. So it's gonna be uh cream with donuts, right? Cream with donuts. So donuts with coffee, cream with donuts, and then this one is going to be, well, it's not gonna have anything. It's not going to have W at all, and it's also not going to have C at all. So it's just going to have some sort of error. Let's see. Coffee, no environment variables. Should that just fail outright? That would just like give us garbage? Because it can start up the program, that's for sure. Or no, does it? The dot slash thing throws me off. I think I'm going to assume it can. Because we have to match it with this anyway. So, but then argc is 1 minus 1. Oh, coffee with coffee. Yeah, coffee with coffee. Because it's always going to use the last argument anyway for if there's no environment variables and if there is an extra argument, well, argc is 1. So 1 minus 1 is 0. It's going to just use the program name for W and C. So that's actually, this one's going to be coffee with coffee. And then this one is going to be coffee with donuts right there. So first one's donuts with coffee. Second one is going to be cream with donuts. And then third one's going to be coffee with coffee. And last one's going to be coffee with donuts. Let's see. Yeah, donuts with coffee, cream with donuts, coffee with coffee, coffee with donuts. Nice. Cool. Okay, so read the news with RSS. RSS feeds. How much time we have? Cool. RSS feeds are a common way for websites to publish their latest news stories. Each RSS feed is just an XML file containing summary of stories and links. Of course, it's possible to write a C program that will read RSS files straight off the web, but it involves a few programming ideas that you haven't seen yet. But that's not a problem if you can find another program that will handle the RSS processing for you. Okay, so I think this doesn't exist anymore. So let's just read it through and just try to talk it over. Sorry, this is just an older book. A lot of things aren't online anymore at this point. Uh, so RSS Gossip is a small Python script that can search RSS feeds for stories containing a piece of text. To run the script, you will need Python installed. Once you have Python RSS gossip.py, you can search for stories like this. Okay, so notice how it sets an RSS feed environment variable. This is going to be a URL. So most likely this Python program is going to take whatever's in the environment variable here, the website, and go into it and then look for the strings pajama death inside. And an RSS feed is kind of like, let's see, let me see if I can show you what an RSS feed looks like. RSS feed example. It looks like this. So an item is basically like a news article, for example. So the title of it, link to it, and then the description. So it's just probably looking for the description or the title, whether or not it has pajama death. Okay. Okay. So the editor wants a program on his machine that can search a lot of RSS feeds all at the same time. You could do that if you ran the RSS gossip.py several times for different RSS feeds. Fortunately, the out-of-work actors have made a start a program for you. The trouble is that they're having problems creating the call to exec the RSS gossip.py script. Think carefully about what you need to do to run the script and complete the newshound code. Okay, sure. So here's all the feeds that we need. So we're going to have to call the program most likely 3 times. Yeah, times 3. And we're going to set the environment variables each time to one of these. Feeds I, equals 0, feeds I equals 1, feeds I equals 3. So I think that's what the loop is trying to do here. It's going to loop over 3 times. Basically, this is going to be what var is going to be. Oh, it's going to just be the environment variable that's going to be set right here. Okay, and then it has to set this up. Okay, to run the program. Remember when we do exec le, we had to create an array of strings. So we'll set the first one to be the environment variable RSS feed equals blah. S would be the current string, the current URL we find in feeds right here. Okay, and then so that goes into var, and then that's basically a string at this point. But remember, we need an array of strings, so we create var inside along with null. Null is required to be at the end. And now, okay, we want to execute Python. Okay, that's great. And this one here, this argument here, is going to be the RSS feed script, RSS gossip.py, this one right here, because that's how we execute Python programs. We use Python space, the argument is actually the name of the script you want. And then, oh, comma, the next one will actually be the environment variables. Yeah, I don't know why I didn't have a comma here, but basically RSS gossip.py and then comma null, which is going to be the end of the arguments list, comma vars. That should execute the program. Exec le in this case. Let's see. Yeah, exec le, RSS gossip.py. Oh, we forgot the phrase. Where's the phrase? Oh, the argument. Okay. And then null to end the argument list, and then vars would be the environment variables. Okay. Well, I guess I didn't see this part. All right. Cool. So when you compile and run the program, it looks like it works. Cool. The newshound program has the RSS gossip.py script using data from the array of RSS feeds. Worked! It didn't work! What about the announcement of the surprise concert? That was on every other news site. I couldn't send my photographers down there. As it is, I was beaten to the story by everyone else in town. So there's a problem with this program, right? The thing is that notice how he's saying here that um, there was actually more data that we could have seen. But the problem is that look at here. Like these sites were never visited. We only visited the first site. Why is that? Well, look, if you think about the loop here, it execs, but this whole program that we're running right now, this one right here, and I'm just like circling around, that's being replaced by the Python script. So then most likely you never get to the second or third iteration. So the second website or the third website to do the same thing. So that's the problem right there. So that's the downside. So that's the reason why he's complaining that there was more stuff that he wanted, but it didn't appear. He only got the first thing. So there is a problem. Although the newshound program managed to run the RSS gossip.py script, it looks like it didn't manage to run the script for all of the feeds. In fact, the only news it displayed came from the first feed on the list. That meant the other news stories matching the search terms were missed. So yeah, we already talked about that. Look at the code of the newshound program again and think about how it works. Why do you think it failed to run the RSS gossip.py script for any of the other news feeds? So basically, yeah, again, exec is the end of the line for your program. The exec functions replace the current functions by running a new program. But what happens to the original program? It terminates, and it terminates immediately. That's why the program only ran the RSS gossip.py script for the first newsfeed. After it had called exec LE the first time, the newshound program terminated. So this loop will only run once. Okay, once it calls this, and if it's successful, that's it. The program that you've executed here replaces your current running program. So what if you want to start another process and keep your original process running? How do you do it? We use a different thing. Instead of using exec, we use fork. So fork will clone your process. You're going to get around this problem by using a system called named fork. Fork makes a complete copy of the current process. So one into two. So basically, you have let's see here. Oh, my pen shut off on. Okay, so where's my pen? Right there. Okay, so basically, you have your program. Why is it long? Okay, you have your process. Okay. What you do is when you call fork, you just create a different copy, new process. Okay, so you create a copy, new process, but it's actually just a copy of your process. Okay, so that's the first thing, and then your program can continue to still run, and this one can continue to still run too. But what if you want to fork with the Python program? Well, this is a copy of your old program. What do we do? Remember, when we fork, we're just creating a copy. It will clone our process. But that's not what we truly want. We want to actually run Python. Okay? So the pattern here. So let's read on. The original process is called the parent process. So this is the parent process. And the newly created copy is called the child process. Okay? But how can cloning the current process fix the problems with exec? Let's see. Running a child process with fork and exec, right? So basically what you're going to do here, at some point, what's up with my pen? At some point, this is going to call exec. Okay, why is it so bloody? Okay. And here, this program is going to call exec. That's where you transition into Python. While this one continues to run. But how do you do that? How do you know which is which? If they're the same process, right? How do you know, like, oh, this process will run Python, this one doesn't? So we'll see. Yeah, if you're the child, okay, so make a copy. The process needs some way of telling which of them is a parent process and which is a child. Okay, so which one is parent, which one's a child. So the fork function call actually returns 0. So fork actually returns a value. It returns an int. Okay, 0 is a child. And then basically what else returns is, let's just say 1, 2, 3, non-zero if it's the parent. Why is that? Well, if you're the, just so you know, the reason why is that this is actually the PID of this one here. So it's telling actually after you fork, you go here, parent. This 1, 2, 3 corresponds to the PID of this new process that you've just forked out. So, just handy for you to know. But if you're 0, if you get 0 back from the fork, that means you are the child process. It's kind of complicated why, like, explain why that's the case. Like, how does the child process even get that 0? But let's try our best to explain. Yeah. So so you're the child process. Call exec. So we know now if the return value of fork is 0, then we know we're the child process. Otherwise, we're the parent process. So we get to continue on forward. Whereas this one will do whatever it needs to do with the RSS feed searching for that current URL. Basically, it'll exec the Python. This one execs. This one continues on calling fork for other processes. So you have two separate. Actually, let me read this again. At this point, you have two identical processes running, both of them using identical code, but the child process, the one that received a 0 from the fork call, now needs to replace itself by calling exec. So I guess this is a good way to think about it. So the parent process clones itself to child process, the child process calls exec, while this one doesn't call exec. So there's a bit of if-else going on here. So now you have two separate processes. The child process is running the RSS gossip.py script, and the original parent process is free to continue doing something else. So we have to update the newshound program. Let's see. Okay, well, let's do some coding on the screen, I guess. Okay, let's like actually code. Is there more actually? Let's see. Okay, no. Okay. Ah. You know what? Let's just read on because we can't even test this thing anyway. So, okay, basically, you can call fork like this. So, PID-T is actually just like a type that's similar to int. It's kind of like a size underscore t when you call size up. So when you call fork, you'll get a PID-T value, and we named it PID. So this PID here is just a variable name. This is the data type. So data type, variable name, and then the value. So fork will actually return an integer value that is 0 for the child process and positive for the parent process. The parent process will receive the process identifier of the child process. So remember, when we call fork, we get a non-zero value, the 1, 2, 3 here. That 1, 2, 3 is actually the PID of the child process. So we get like a 789 or 555. Those are PIDs for the cloned processes of that parent. So let's skip that. Look at the answer. Okay, cool. All right, so let me try to explain. You know how you have this loop here that iterates 3 times? So basically, we built the environment variables. We know that. But then the next thing we want to do is we want to fork. So we want to clone itself. Well, guess what? When we clone a process, Okay, when we clone a process with fork, that process, if you think about it, it's running. It's running. But what code is it running? It's running the same code, except that now it picks off where the original one was. For example, the next line here, right? That clone process actually starts from there too, but it gets its own set of registers, variables, and everything else. So it has like an image of its own, like it has its own set of things to start manipulating now, but it starts at the same spot. The only thing it gets different is like file handles and I guess network. So I don't know, but something like there are certain things that your clone process, and I think we'll learn this deeper when we learn more advanced things. But basically, when you clone a process with fork, you start off at the same exact spot as the parent when you're the child process. But as a child process, you get your own set of memory. Let's just say that. You get your own set of memory. So then this PID right here is actually going to be a different value for the child process. And then for the parent process, it's going to be a different value. For the parent process, since it's the one that called fork, it was original one that called fork, of course PID is going to be assigned something. Naturally, if you're the child and you start from here, well, PID is unassigned. It's 0 at this point. So that's how you know that you are the child, because you didn't have this PID assigned. Okay? And of course, if PID is -1, meaning that the only way that could be a -1 if you were the parent that called it, you would get a non-positive number. That means something happened. You couldn't fork the process. But anyway, so if you're actually the child process, it turns out if your PID is 0, it means that you are a child and you execute this. So notice how it does the exec LE stuff right here. That's it. And then next, it'll just die when it's done. It'll just get replaced by this Python thing. But going back to the parent here, it's gonna, since this was not true, it's gonna go next iteration to I equals 1 in this case, so we'll go 0, 1. It's gonna run the second URL and it's gonna fork again. So basically what we have is something like this. So we have the parent. I don't like doing this. I just like drawing freehand. Okay, so we'll have the parent here, where at this point we have parent I is equals to 0. It's going to fork a child, and that's going to eventually get taken over as Python, the Python script. Okay, but then when that's, and then after that, the Python script runs and it kills itself. But then the parent is still running, so then I is now actually I shouldn't draw it like that. So parent's running, parent gets I equals 3, or I equals 1. Why did it say 3? And then it's going to fork again to a new child process. And that one's going to run with a different URL. So this is URL 1. This is going to be URL 2. And that's going to fork or exec into Python. And that will eventually kill itself because it's done. And then going back to the parent again, next iteration, I equals 2. It's going to fork child with URL 3. And this child's going to call exec. Let's go down here. With Python. And that's going to run and kill itself. So that's like the like main idea of how this works. And I guess don't worry if it's hard to understand. Just kind of know that fork clones the current running process, and it's because of that you can leverage that fact to call exec to do what you need to do on the child process. And this is actually how operating systems create new processes, by the way. Okay, anyway, now you compile and run the code, this happens. So it gets everything now. Hey, that's great. I'll send my photographers down to the premiere. By forking a copy of itself and then execing the Python script in a separate process, the newshound program is able to run a separate process for each of the RSS feeds. And the great thing is that the processes will run at the same time. Yeah, actually, this is kind of misleading in that I made it look like they're running one at a time, but really they're getting forked successively, and it doesn't matter. This one doesn't have to finish before this one forks a new one. It doesn't know. The parent doesn't know, so it just forks, and then it's up to these guys to finish at various moments in time. So it's actually not finishing in order at all. Okay. So that's a lot faster than reading news feeds one at a time. That's kind of like multi-threading in this case. By learning how to create and run separate processes with fork and exec, not only you can make the most of your existing software, but you can also improve the performance of your code. So does a system call run, does a system function call run programs in a separate process? Yes, but the system function call gives you less control over exactly how the program runs. Okay, isn't forking processes really inefficient? I mean, it copies an entire process and then a moment later we replace the child process by doing exec? Yeah, operating systems use lots of tricks to make forking processes really quick. For example, the operating system cheats and avoids making an actual copy of the parent process's data. Instead, the child and parent processes share the same data. Yes, so they share the same data. I think they share the same files. I said earlier that they didn't share the same files, so that doesn't make sense. They share the same files too, but they don't share memory. Like they don't share like stack and like register stuff. Okay. Yeah, I know I got that backwards earlier. Yeah, so what if one of the processes changes some data in memory? Won't that screw things up? It would, but the operating system will catch a piece of memory that's going to change it and then make a separate copy of that piece of memory for the child process. That technique sounds quite cool. Does it have a name? Yes, it's called copy on write. It's is a PID just an int. It depends on the platform. The only thing you need to know is that it will be some integer type. So PID is just kind of like an integer, a number. I stored the result of a fork call in an int and it worked just fine. It's best to always use PID_T to store process IDs. If you don't, you might cause problems with other system calls or if your code is compiled on another machine. Why doesn't Windows support the fork system call? Windows manages processes very differently from other operating systems, and the kinds of tricks fork needs to do in order to work efficiently are very hard to do on Windows. This may be why there isn't a version of fork built in. But Cygwin lets me do fork in Windows, right? Yes, the gurus who work on Cygwin did a lot of work to make Windows processes look like the processes that are used on Linux, Unix, and the Mac. But because they still need to rely on Windows to create the underlying processes, fork on Cygwin can be a little slower than fork on other platforms. So if I'm just interested in writing code to work on Windows, is there something else I could use instead? Yes, there's a function called create process that's like an enhanced version of system. To find out more, go to msdn.microsoft.com and search for create process. Yeah. Won't the output of the various feeds get mixed up? Yes, as the operating system. Wait. The operating system will make sure that each string is printed completely. Is that true? Oh, wait, no, I need to read that carefully. The operating system will make sure that each string is printed completely. Okay, so the strings outputted from each process, they won't get jumbled up with other processes. So all this is grouped into one, all this output is grouped in another, all this is grouped in another. Okay, yeah, but they still all run at the same time. System calls are functions that live in the kernel. The exec functions give you more control than system. The exec functions replace the current process. The fork function duplicates the current process. System calls usually return -1 if they fail. Okay, so you know how like there's a lot of memory type of function calls that we do that return null if they fail? Well, system calls will return -1 if they fail. So that's a pattern. Anyway, failed system calls set the error node variable to the error number. Okay. And And we finished another chapter. Yay. Interprocess communication. We'll leave that for next time. All right, long one today, but thanks for hanging out. Bye.